What if I told you that a magnet made a clock run 41 seconds faster over 4 months? No spinning satellites, no rockets, just a magnet shaped like a pyramid. That's not a hypothesis, that's a measured result. And by one comparison, the effect was over 9,000 times stronger than the time correction NASA uses for GPS satellites. Stay with me, because by the end of this video, you will understand why this is fascinating. But before we get to that experiment, we need to understand two things: how magnets actually work, and why a pyramid-shaped one might behave differently than the fridge magnet in your kitchen. Ken Wheeler's framework looks at a magnet very differently from a standard physics textbook. Instead of treating the two ends as plus and minus, he treats them as two opposite kinds of behavior in a single field. One end mostly pushes energy outward, the other mostly pulls it inward. The outward pushing side spreads energy into space like a spray nozzle. The inward pulling side gathers the energy back toward a hidden middle layer where the field is most balanced, also known as a block wall. In this picture, two magnets aren't literally grabbing and pulling each other. Each one changes the pressure in the invisible field around it. Between certain arrangements, a calm, low pressure zone appears in the space between them, and both magnets move toward the shared zone, the way the air flows toward a vacuum. What we call attraction is actually motion toward the quiet, low pressure region, not a mysterious pulling force. This view is different from mainstream physics, so it should be understood as an alternative. Field-based way of thinking about magnets, not the standard model taught in universities. It's useful for purposes because it describes magnetic fields in simple pressure language. One side spreads out, the other side squeezes in, and things move from high pressure toward low pressure. Shape doesn't change the basic inward-outward story, but it changes how that behavior shows up in space. A pyramid magnet is the same kind of field system as a block magnet. The difference is its sloping sides and pointed tip act like a nozzle. With a regular block magnet, the outward pushing field spreads over a broad, flat face, wide and even. With a pyramid, the same outward push gets guided up and squeezed into a much smaller area at the apex. So the field there is far more concentrated. Very close to that point, the field pressure is much higher than above a flat block. But because it's packed so tightly, it also falls off faster with distance. Think of a block magnet as a wide sprinkler head and a pyramid magnet as a high pressure nozzle. Same underlying field dynamics, but the pyramid focuses the outward push into a sharp jab at the tip instead of letting it spread broadly. That's why a pyramid magnet becomes especially interesting when you care about what happens right at a point in the field. Here is the hypothesis. Drawing loosely on Ken Wheeler's claim about field pressure and on electrical engineer Oleg Jefimenko's work on electromagnetic retardation, there's a working idea linking how tightly a field is packed to how fast time effectively runs in that region. You don't get faster or slower time because space-time bends like in Einstein's relativity. Instead, time is treated as something that emerges from electromagnetic field intensity and its gradients. Under that idea, a sharply compressed field zone behaves like a region of fast time, while a spread out, weaker field behaves like slow time. Applied to our pyramid magnet, the high Gauss top, where the field is forced into a small dense pocket, wouldn't just be the strongest part of the magnet. It would sit in a bubble where clocks could, in principle, tick slightly faster than at the wide, low Gauss base. This goes well beyond textbook electromagnetism, but it's the lens we are using here. Compressed fields as locally faster time, rarefied fields as locally slower time. Alright, so that's the theory. Here is what actually tested. We used two truncated pyramid-shaped neodymium magnets, grade N42 and 45. The apex, a small 1-inch square at the top, carries the south end, measuring roughly 6,000 Gauss. The base is a 2-inch square, carrying the north end. Same total field, spread over 4 times the area, dropping to around 3,300 Gauss. Both pyramids ran continuously for 119 straight days, from January 27th to May 26th, with a clock on the top and another at the base of each. 4 quartz wristwatches were used, 2 per magnet. Magnet 1 showed a net drift of 39 seconds between top and base. Magnet 2 showed 43 seconds, an average of 41 seconds across both. That works out to a drift rate of roughly 344,000 microseconds per day. For comparison, GPS satellites need a correction of only about 38 microseconds per day for real, well-established relativistic effect from orbital velocity, making this result over 9 times larger. So that's the confirmation, and it's an exciting one. What the numbers are consistent with, in plain terms, is time running faster at the top than at the base. So go back to the pressure picture. The top is where the field gets squeezed into a dense pocket, while the base is where it spreads out thin and weak. Here's the piece that ties it together. When a field gets squeezed into a smaller space, it doesn't just get stronger, it has to spin faster to push the same amount of field through a tighter opening. Think of a skater pulling the arms during a spin. Same energy, smaller space, faster rotation. Think about water running out of the bottle. You spin the bottle, water runs faster. That faster spin at the top is what's being treated as faster time. Magnetism's timing character tied to this internal spin rate. So when the field compresses and spins up at the top, the clocks sitting there aren't just in a stronger field. They are in a faster ticking one. There is a name for this, a temporal blue shift. The same basic idea as compressing light waves toward higher frequencies, except here is time itself getting compressed. The south-seeking apex is where that compression and spin up happens, producing the accelerated blue shifted time. The north-seeking base sits in the white thinned out field, where time runs comparatively slower. Well, now here's the detail that changes the picture somewhat. This wasn't a single clock pair, obviously. Clock pair. It was 2 independent magnets, each with its own apex and a base watch run at the same time, and both magnets show the same direction of drift. Apex ahead of base with a similar magnitude, 39 seconds on one, 43 seconds on the other. That consistently mattered. If there were just random manufacturing tolerance between individual quartz crystals, you would expect the direction to be a coin flip each time, not the same result twice in a row. So we can set aside pure random noise as the explanation. But consistency across 2 trials doesn't automatically confirm that something exotic is happening, unfortunately, or fortunately. For instance, consistently stronger magnetostriction or warmer apex due to how the pyramid shape concentrates field and heat. Either of those could produce the same direction of drift we're seeing. So where does that leave us? To test this properly, you will need a tighter setup. Atomic clocks, immune to magnetic interference altogether, not sure if it's even possible, honestly. Temperature logging, running continuously at both apex and base so that variable gets ruled out rather than argued about. And multiple magnets, different shapes, tested against each other. Not just pyramids, but cubes too, to see if the effect actually scales with field compression the way the theory predicts. So the implications go well beyond the curiosity. You would be looking at the possibility of accelerating biological or chemical processes simply by placing them in a compressed field zone. And further out, some genuinely speculative time manipulation concepts that lead on the same compression logic. And with that, I want to say a big thank you goes to Mark Sokol and his team at Falcon Space for running this experiment and patiently waiting on the results. This wouldn't happen without their help. You'll find links to the exact clocks and pyramid magnets used in this experiment, as well as a sketch of the experimental setup in the description below. If you want to help push this from anomaly to answer, that's the place to start. Replicate it, tighten the controls we talked about, and see what holds up.